okay? And so to prove all of this, I'm going to erase what I just wrote, all of this stuff about k and the wave number, because I want to make some room here. Okay, I'm just going to add a new slide here at the end. So many slides here. Okay, so here I've just got a blank sheet now, 2 blank sheets. So I'm just going to write here continuation from slide 18, okay? That says continuation. You heard what I said. Okay, and so what I want to do, that solution that we just came up with, okay, let's rewrite that. Psi x equals cosine kx, where k equals 2m e minus v all over h bar squared and that's all square root. So there's a game we're going to play here, and we're going to kind of go in circles to see if solutions we come up with are confirmed by other solutions. Okay, so for example, we recall the de Broglie relationship. So we were working here really with the momentum operator, which is like a part of the kinetic energy operator, right? And we know that the de Broglie wavelength is h bar divided by lambda. So is this solution that we've come up with consistent with de Broglie's wave equation? Okay. And so I'll just remind you that this, when we have total energy, E, I'm just going to write like E total, okay? That's going to be equal to the kinetic energy, EK, KE, T, kinetic energy, plus V, right? Total energy, okay? So then we know that, therefore, and I'm just going to put in parentheses E from our Schrödinger equation, okay? So then we know, doing some algebra here, that E minus V is going to give me the kinetic energy, right? The difference between the total and the potential is the kinetic. All right? So that means I can rewrite this wave number solution up here as 2 times m times the kinetic energy, okay? And that is all divided by h squared and square root, okay? So if I rearrange now and solve for kinetic energy, I'm going to skip a few steps and just write that directly. We know EK is going to be equal to k squared times h bar squared, all divided by 2 times mass, okay? Where we know that that is also equal to p squared divided by 2 times mass, right? So this p squared divided by 2 times mass is another way of writing kinetic energy, right? Which comes from 1/2 mv squared, okay? So now if I rearrange this right here and do some algebra, you can see the 2 mass and the 2 mass is going to cancel. And so I've got k squared times h bar squared equals momentum squared. And of course, I can take the square root of both sides and get k times h bar equals momentum. And this is really cool because recall, you know, k for the solution for the Schrödinger equation, k equals this, 2 mass times kinetic energy divided by h bar squared, all square root. But we also know, right, just from my standard cosine function, that k, the wave number, just equals 2 pi divided by lambda, okay? So now if I substitute that result here, 2 pi divided by lambda, and we also know that h bar is just h divided by 2 pi, okay? Then now that's times h divided by 2 pi, And look at this. This is awesome. 2 pi and 2 pi cancel, and we get momentum equals h divided by lambda. Okay, so yes, the solution is confirmed by the Schrödinger equation. And also we can see this is why we use h bar, because it has that 2 pi unit in it already. And this is going to allow us to make those direct calculations from energy to wavelength to wave number, just like I showed you in the lecture 1 video, okay, reviewing our units, okay? So very cool stuff. So I think that is actually a good place to stop, and I will see you in lecture video number 4.